Howdy, my name is Lieutenant Jacob Springer, and I'll be going through EE301 Lesson 1. It's the very first lesson, and also welcome to my guest bedroom, which is where I'll be recording during this interesting time of coronavirus. So Lesson 1, voltage and current. If you took Physics 2, you're probably familiar with these topics, but before we even get into voltage and current, let's just talk a little bit about the topic of units. Right here it says dimensional analysis. Now we use units all the time. If I say it takes me 5 to walk across the yard, that doesn't really mean anything to you without knowing that it's 5 minutes. It doesn't take me 5 hours, it doesn't take me 5 seconds, it takes me 5 minutes. How many miles is it from Washington, D.C. to Annapolis, right? And so the units give it context to what we're describing. So an example of units here and how to convert from one unit to another is we have yards going into meters. Now, if you have in other classes possibly done something like railroad tracks, it's essentially just canceling the equivalent unit. So here's yard, convert it into feet, cancel out the yards. We have 3 feet, we can cancel out the feet into meters. We multiply 2.5 by 3 by 0.3048, we get 2.286. So there's an example of how we easily can cancel out units. Now something else, you can see where the decimal is right here, 2.286 meters. If you're familiar with kilometers, well, what is kilometers except 1,000 right there? See the 10 to the 3, that would be 1,000 meters. So kilometers, that's something we'll be using in this class, 10 to the 3 kilometers. We'll be using milli a lot as well, 10 to the negative 3, and micro. Those are probably the most common ones. We'll get into mega a few times, nano a few times, but for the most part, we'll be sticking to those units. I'll skip example 2 here as we keep scrolling down, because I think that these idea of canceling out the units you can do with just a little bit of practice. But this is a better example here of how we don't want to see the answer. So in some classes, perhaps they're looking for scientific notation, and occasionally maybe the homework will still have you put it in scientific notation. But on any paperwork, please put it in this good form. 15 times 10 to the negative 5 is not good. 150 microseconds, that's good. And the reason why is because you wouldn't say that. Imagine you're on a ship and someone says, how many amps do we have going through? And you say 10 times 10 to the negative 3. That would be really obnoxious if we spoke that way. Or if we just said 0.0000001, that would also be obnoxious. So please always put it into the engineering units. Here's an example of how you could do that. 15 times 10 to the 5th, 150 microseconds. So in electrical engineering, or in electricity, we're talking about the movement of charge. And if you think back to physics and we think about positive and negative charges repelling each other, at the end of the day, what we're doing in this class is we're moving these negative charges, or electrons. So we're transferring electrons. And now the charge on one electron is very, very tiny. Look, times 10 to the negative 19th. Or in 1 coulomb of charge, which would be Q. Q has a unit of coulombs. And so units I put in the brackets like that. And so there's 1.602 times 10 to the negative 19th coulombs per electron. Or there's this large number, 6.24 times 10 to the 18th number of electrons in 1 coulomb. So anytime in electricity, we're moving lots of electrons. So we'll actually just stick to moving charge, or moving one charge of Q in coulombs. So now let's talk about voltage. Voltage is the work that is required to separate the positive and the negative charges from one another. But the key word with voltage is right here, potential difference. If we think of it as an electrical potential difference, I have 2 points along a circuit, and we're going to get to circuits later, but we have 2 points that are electrically separated, and how much work or energy does it take? It takes 1 joule of energy to move 1 coulomb of charge. That's its electrical potential difference. So its volts is equal to, the W there is work, right? Work or energy. We'll use those interchangeably. Work and energy. How many joules does it take to move 1 coulomb? That's voltage. This equation right here is on your equation sheet. If you look, V equals W over Q. And you can also see that we have the charge right there with the electrons. So far we've covered these 2 formulas. Let's keep moving down the page. We'll work problem number 7 here. It says that 600 joules is required to move 9.36 times 10 to the 19th electrons from one point to another. Now that's a large number. It is in scientific notation. Let's not worry about that. Let's just, for this example, plug in the formula and see how much work is required to move however many coulombs. So we have 600 joules is what is required to move 9.36 times 10 to the 19th. We can do our conversion that we say 1 coulomb is 6.24 times 10 to the 18th. Multiply that out in a calculator and we get 40 volts. So that is the electrical potential difference that is needed to move that amount of electrons. Now current may be even a little bit easier to understand than voltage, because electrical current is just the rate that that charge is moving. So here's Q, it's charge, it's moving time per second. So it is the rate of flow of coulombs of charge per second. So initially, and this is just for terminology, everyone didn't understand 100 years ago how electricity flowed as far as the electrons, the negative charges moving. So they began drawing the current flowing out of the positive side. This is called conventional current direction, and it's what we will be doing in this class. Actually, the negative electrons flow out of the negative side, and they flow toward the positive side is how the actual electrons flow, but we will be using conventional current direction. So always, always, always draw your current coming out of the positive end. Positive end is where the current flows out of. Here's a description in problem number 8 of actual electrons moving. I'm just going to move on through because everything that we'll be doing will be in conventional current direction. And that's the end of lesson 1. So remember, draw positive current out of the positive end or positive side of a voltage source. And with that, there's lesson 1.